million node points. So it's a huge number of node points. At each node point, all the transport equations are solved in each iteration. Flow solution method, large eddy simulation approach, a CFD technique. Turbulence model, again standard Cape Silent model was used. These are the boundary conditions. So I got a velocity inlet boundary condition, then the outlet, pressure outlet, open boundaries. Later on I will show you what these boundaries are, symmetry, and the cricket ball was taken as a non-rotating ball. So basically I was modeling non-rotating cricket balls, not rotating cricket balls. So that was one of the limitations. So this is the computational model. Here this is the 3D model. This is the center plane of the 3D model. So this is the 2D center plane. Here I have the cricket ball in the middle. So this length is 400 millimeters. This is 600 millimeters. So this was kept 150 millimeters from the inlet boundary. So this is the inlet boundary, this is the outlet boundary. These are the symmetrical boundaries. So the resolution of the mesh was changed from one point to another. Here we have a very finer mesh. Here we have a coarse mesh, because most of the changes are taking place in this area. So I had a very fine mesh here to accommodate the drastic changes that are taking place in the vicinity of the cricket ball. And then the triangular volume mesh with 2.2 million nodes. Why I use this type of this number of nodes is that you have to have a compromise between the accuracy of the solution and also the computational time and cost. So you have to optimize your solution. For optimizing, what I got was, this was the optimized number of nodes for the solution. And then this was run. So actually we don't have very fast computers to do this. So this was run on a normal PC. And these are the capacitors, 3.2 gigahertz and 4 GB RAM. You have to have a bigger RAM, fast processing speeds to do this. But of course, we are compelled to do this. So this is the iteration, the graph. So iterations are taking place, and residuals or the errors are here. So once the errors are down to a certain value, the solutions are, we can consider them to have converged. So let me show you some of the simulation results. Total pressure, yeah. This is when the seam angle is 0. So you can see there is a symmetrical distribution of flow. So no pressure variation is there. So here we cannot expect any side force to take place. This is angle 30. You can see there's a high pressure zone here, low pressure zone here. So the side force is in this direction, in the direction of the seam orientation. So the side force is 0.64 Newton for optimum conditions, and that optimum speed is 112 kilometers per hour. Later on I will tell you why this value is low. Conventional swing is, whatever the commentators say, is only a tool that can be used by medium fast bowlers, not by fast bowlers. This is for 45 degrees where you have optimum conditions. The angle is larger than 30. Speed of delivery is only 106, where you have optimum conditions for swing, and the side force is 0.55 newtons. These are intensity profiles. At 0, you have a very symmetrical flow pattern, so no swing takes place here. Again, at 30 degrees, you have more turbulence here. Yeah, you have laminar flow in this direction, turbulent flow in this direction. So definitely there will be pressure reductions here, and swing takes place in this direction. So here also you have less turbulence, so swing force is less here. So this graph will give you some idea of the swing force. So here at 45 degrees you have highest swing force at 106, here 112. But unfortunately after 120 you don't get any conventional swing for 45 degree. After 130 you cannot obtain any conventional swing for 30 degree angle. Conclusion, as I said before, 30 degree angle optimum delivery speed is 112, and it will be 40% of the total weight of the ball. For 45 degree it is 106, and it is less, the conventional swing force is less than 30 degree angle. During the optimum conventional swing, shiny side of the ball experiences laminar flow, the rough side experiences turbulent flow. And the difference of pressure will cause the conventional swing. When the angle is 30 degrees, there will be more turbulence, more pressure reductions will be there on the rough side, and there will be more conventional swing. It has been a challenge to model this scenario using CFD software. You cannot sometimes predict the actual problem on the computer. There will be flow properties changing from actual situations, turbulence, but however, the analysis is in good agreement with the analysis of Mehta, who was an Indian who made all these analyses previously, but using only experimental techniques, not using CFD. So beyond 130, when the angle is 30, swing will stop, and also when you have a higher seam angle like 45, you can have low side force, and also the main drawback is absence of measured data for validating the primary variables, because I had only computer simulation, no experimental data available to validate the primary variables. But of course, if you have a wind tunnel with smoke injection and flow visualization capabilities, the model can be further refined to obtain more correct, accurate predictions. Thank you.
Thank you, Priyanta. Bandara is a graduate from Moratuwa. He's from Moratuwa, University of Moratuwa Mechanical Engineering, and he has also a large number of publications. His main interests are, well, he has the first degree as well as the second degree MH from University of Moratuwa Department of Mechanical Engineering. His work experience is tremendous in terms of teaching. And thank you very much, Bandara, for your presentation, along with your partner is Mr. Karnrad. Okay, fine. Thanks, Karnrad. Thank you very much for that interesting presentation. With that, we get on to the third presentation. Fourth one. Where is that one now? We have Mr. Gunaratna, the last speaker, to present on his fast algorithm for multi-point evaluation of invariant polynomials.
Okay. Thank you very much, madam. Good afternoon, all. I am the last presenter for all engineering session in 2012 symposium in KDU. I may hope I'll be given more time.
Sure, you have.
Anyway,
go ahead.
Let's start. I'll be presenting on the implementation of a fast algorithm for multi-point evaluation of univariate polynomials. The introductions here, f is a univariate polynomial of degree n-1, and c is a set of n complex numbers. The direct computation of f at all the points in C required O(n) to the power 2, which is a computational complexity that indicates the number of arithmetic operations required for the entire computation. But for a large n, this is a prohibitive cost for practical purposes. Due to the significant number of applications in the field of engineering, medicine, weather forecasting, and spectacle methods for solving the differential equation, the necessity of fast algorithm for computation of the univariate polynomial arises. The computational complexity of such fast algorithm we study is n log to the power n arithmetic operations. We had to go in more detail in these algorithms because the proof or construction of this algorithm had some considerable mistakes where no one has proved or no one has made them correct. And also, to the best of our knowledge, there is no any other algorithm faster than this for the univariate evaluation of the polynomials. And also, these algorithms depends on the very well-known past computational methods. You see here, and also our objective is to implementation of these algorithms is to examine the numerical efficiency and the numerical stability of the algorithm. And this is a discrete Fourier transforms. You can see this is a very well-known Fourier transforms, and it has a great demand in the field of engineering, medicines, and other fields also. Again, here computational complexity is O(n) to the power 2, and it is again too much for practical purposes. Then the other algorithm accompanied with this algorithm in the inverse discrete Fourier transform. We can define that one in similar manner. The computational complexity of these dual algorithms contains O(n) to the power 2. So fortunately though, one past algorithms available for the computation of the both DFT and IDFT, which is a very fast algorithms and very well-known algorithms. It is called the past Fourier transform. The techniques of the past Fourier transform depends on the standard techniques of the conquer and divide approach. That is, we divide the entire problem into the similar subproblems, smaller subproblem as long as possible, and we start the computation from the smaller subproblem, and we keep on computing until we accomplish the original size of the problem. And also, this algorithm actually made the cause a drastic revolution in the field of engineering, especially in the field of electrical and electronic engineers. This was found in 1965. Soon after being found this algorithm, over the 2,000 papers, especially in the engineering, published based on this algorithm. And the computational complexity of this algorithm is n log n. It is a so